formation and evolution. Okay, so starting off with Comet NEOWISE. This is an image of NEOWISE that was taken from Germany 2 days ago. It's a bright, naked eye comet that is now visible. So this particular exposure time is 15 minutes. And so you can see a lot of detail here within this image. You can see, can you see my pointer moving?
Yes.
Yeah.
Okay, good. You can see the head, the nucleus of the comet is just off the screen here, the brightest part of the comet. And then this sort of pinkish tail back here is the dust tail. Okay, so this pinkish tail is the dust tail, and then this bluish tail is called the ion tail. And these are features that most comets have. And so I'm going to just talk about what those mean in a second. Let's see, I can't. There we go. Okay. This again is Comet NEOWISE, taken by a friend of mine in Flagstaff, Arizona, about a week ago when it was a morning object. It's just a real spectacular object. It's not very often that we get to see a naked eye comet. So if you do get a chance to go out and see it, then I really do suggest that you do so. It's easiest to see when it's in a dark sky site. So people who live in cities will have a harder time seeing them. But if that's the case, then bring some binoculars. They'll help a lot. NEOWISE was discovered in March, on March 27th, by the NEOWISE satellite. Comets are named after their discoverers. So this is Comet NEOWISE because the satellite discovered it. And the NEOWISE satellite is the Wide Field Infrared Survey Explorer, which has been sort of repurposed to look for near-Earth objects. And so that's the NEO part and then the WISE part. It doesn't have a very large mirror, it's only 16 inches, but it has the advantage of being in orbit around the Earth. And so it doesn't have a lot of the light pollution problems that you might have down on the, from an earthbound observatory. And down in this right-hand corner here, this is the Discovery set of images where you can see the comet here in red moving against the background stars.
All right, okay. Could you hold on just 1 second? I'll check with my husband. You can bring it out.
Okay. If you
That's
have
fine.
not,
I don't mind waiting.
if you have not yet seen
I'll motion through the door.
Okay, he's good with it. He knows you.
If you have not yet seen it, okay, if you have not yet seen the comet, then shortly after sunset, when it gets a little bit darker, around 9 or 10 local time, you can look toward the northwest and you can use the Big Dipper as a pointer to the comet. So tonight it would be down here, still a little bit low to the horizon, but it's getting further away from the sun as it goes on, and so you might have a better shot. However, as it gets further away from the sun, it also gets fainter, and so the earlier you go out to see it, the better, but then, there's a trade-off because it'll be hard to see when it's when it's too close to the horizon. Okay. This is the plot of the comet's brightness so far. This is in magnitudes, and magnitudes are this really odd inverted scale. So lower numbers are brighter and higher numbers are fainter. And so when the comet was discovered, it was pretty faint, and then it was starting to brighten. And then over here, July 3rd is when it actually came closest to the sun. It came very close to this, quite close to the sun, closer than Mercury. And that is when it was at its brightest time. And now it's been slowly fading, and we expect it to fade more. Certainly by August 1st, it should no longer be a naked eye comet, but that may also happen before. We never know. Comets are kind of like cats. They do their own thing. We know what they should do, but sometimes the nucleus will actually break up, and then it will disappear really quickly. If this comet holds together, then it will possibly follow this fade line here, and we'll still be able to see it for quite a few more weeks. But we'll have to see. We just don't know. For those of you who know orbital mechanics, these are the orbital elements of comet NEOWISE. It has a semi-major axis of 360 astronomical units, where 1 astronomical unit is the distance between the Earth and the Sun. So the orbit of this body goes all the way out to 715 astronomical units. So it gets very far away from the Sun. So it spends most of its time in the outer reaches of the solar system where it's very, very cold. It has an eccentricity of almost 1. So this thing, when it comes into the Sun, it comes in and then goes back out almost on the same path. Its perihelion was closer than Mercury's orbit, and its aphelion is, like I said, is very far out, and its period right now is almost 7,000 years. Its close approach to the Sun actually changed its period. Before, as on its way in, its period was only 4,500 years, but now it's 6,800 years. So this is what the orbit diagram looks like. So NEOWISE came in this way and is going out this way. And this is for today. So this is where NEOWISE is today. It still hasn't passed the orbit of Mercury. And then this is where the Earth is, but it's coming out pretty fast. If we, you can see that all we have here, this is just the inner solar system, Mercury, Venus, Earth, and Mars. If we want to see what this looks like in a larger context, I'll zoom out to the next one. And all of the inner solar system is now in here, and we have Jupiter, Saturn, Uranus, and Neptune, and you can see how narrow this orbit is. And then I'm going to zoom out one more time, and then you can see this is our entire solar system in here, and then the NEOWISE goes all the way out here, where there's really not much of anything going on. So what is going on with NEOWISE? Well, when it gets close to the Sun, it does something like this. This is not a picture of NEOWISE. This is a picture of comet Churyumov-Gerasimenko taken from the Rosetta spacecraft. And we, in order to get a picture like this, you need a spacecraft to be sitting right next to the comet. We don't have one next to NEOWISE, so we're going to just use this as a proxy. So a couple things to notice here. This comet surface here, you can see some of these faint streamers coming off of this comet surface. And what is happening here is that the ices on the comet surface are getting warmed by the Sun because it's close enough to the Sun to do so. And then as it gets warmed by the Sun, those ices will sublimate. They'll turn from ice, they won't go through a liquid phase, they'll just go directly into a gas phase. And that's what you're seeing happening here. So all of the ices on the surface are sublimating, they're coming off in these gas streamers. As the gas comes off the surface, they often drag some of the dust particles with it as well. It also has a strange shape that I'll get back to later as well. Now, when you look at this in a larger sense, right, this is what it looks up really close up. But when you sort of zoom back out, what does it look like? Well, what a comet will look like is it will have, some sort of a nucleus with a fuzzy coma around it, and then it will have a tail. And what we saw in Churyumov-Gerasimenko, all of that stuff coming off the surface, that becomes the coma and that becomes the tail. Now, comets will often have 2 tails. They'll have a dust tail and they'll have an ion tail. The dust tail sort of follows the path of the comet, and then the ion tail is composed of ionized gas molecules, and that when the solar wind goes past them, it picks up those ionized particles and just takes them out. So the ion tail always points exactly opposite the Sun, but the dust tail kind of tells you where the comet came from. And you can see that in this cartoon here, where the dust tail is here. Sorry, this is the ion tail, and then the dust tail is here and kind of curving, and the ion tail is always pointing directly away from the Sun, which is the center here. There are also some larger particles that are kind of shed by the comet as it moves along its orbit, and we can't see those when we look at the comet in the night sky, but we can detect them because they end up being meteor showers at a later time. So when the Earth, you can imagine as the comet is moving along, then it's shedding particles all along its orbit. And then if its orbit happens to cross the orbit of the Earth, then those particles will enter the Earth's atmosphere and we will see them as a meteor shower. So comets have a lot to do. They're beautiful to look at in the night sky, and they also, have affected our history because people have always been wary of meteor showers because they didn't know where they came from. So if we look at a comet, one of the things we may want to know is what is it made out of? What is the comet itself made out of? What are their tails made out of? This is a picture of Comet Hale-Bopp, which, and the picture was taken in 1997. It was another very bright naked eye comet. And I'm just going to use this one as an example to show you what the compositions are, what types of compounds are in these various areas. So if we look at the ion tail is composed of ionized gas, which the name implies. The dust tail, this orangey, yellowy one, is composed of dust and gas. And then the nucleus, which we can't see here because it's covered by all of the emissions from the coma and the tail and whatnot. The nucleus is really composed of rock and some volatiles and some hydrocarbons. So this is a really interesting thing because first of all, comets have the name of dirty snowball. So you can, that's to reference its composition. It's made out of these volatiles like water ice. And it has some dirt and dust in it as well, some amount, some more or less, depending on where it was formed and what its history has been. And it also has some more complex hydrocarbons in it. And so over the years, people have been, wondering what is the, how do comets affect the Earth and life on the Earth? Could it have brought, material to the Earth? And the answer is yes. Comets definitely have brought material to the Earth. Other objects in the solar system have brought material to the Earth as well. So I'm going to just shift right now to really try to make this bridge between comets and, just in a general sense, volatiles within the solar system. So volatiles are compounds that can be liquid or gaseous at planetary temperatures. A very common volatile is water. So if we think about it, here on Earth, water is a volatile because it can be in its liquid state, it can be solid as ice, and it can be gas as water vapor. If we get out to Pluto, however, at 40 astronomical units, water is no longer a volatile. Water is a bedrock on Pluto. So if you've seen any of the images from New Horizons, the mountains, the little mountains that we see on Pluto, those are basically the base of those are solid water, which at those temperatures, nothing happens to it. It's a rock at those temperatures. But at the Earth, nitrogen is a gas. On Pluto, nitrogen is a solid. On the Earth, carbon dioxide, carbon monoxide, ammonia, and methane are all gases. But as you go further out in the solar system, these become solids because you get colder as you get further out in the solar system. But these are all volatiles. And so one of the things we want to know here is, where do these exist in the solar system? Because volatiles are so important to life on Earth, and they may be important to life in other places within the solar system as well. So if we know where these volatiles exist, then that will tell us, where life could have evolved in the past and where to look for life if we, sending spacecraft out. So if we look here, this is a spacecraft image of Mars's north polar cap, I believe. Yeah, north polar cap. And this, you can see all of these white deposits here. They're actually, these are deposits of carbon dioxide and water ice. And so Mars has these cycles, and it will, these polar caps will shrink and grow depending upon the seasonal cycles. And the water ice is actually underneath the carbon dioxide ice. The carbon dioxide ice comes and goes more frequently. Okay, so we know we can find some volatiles on Mars. There definitely are spacecraft missions, in progress and also planned to look for signs of life on Mars as well. On the Earth, we have this water cycle that allows life to exist. As we get further out in the solar system, if we're talking just about water, then we don't always go through the same cycles. The solid ice doesn't always melt into water and then evaporate into steam. Instead, depending upon the circumstances, the solid ice will just directly sublimate into a water vapor. And so we just have to be aware of these different phase changes and how they progress at different temperatures and pressures within the solar system. So if we're looking specifically for water, which we know is a component of comets, obviously we know that the Earth has a lot of water. We can see it here in this lovely blue marble image of the Earth taken from spacecraft data. One of the really interesting things that NASA has done here is to look at how much water really is on the Earth. I mean, it looks, 70% of the surface of the Earth is covered with water, but how much water is there? So here's another image put out by the US Geological Survey. If we took all of the water on the Earth and we combined it into an equivalent sphere of water,
That's my floor.
this is the size of the sphere of water. So this is all of the water that is on the planet Earth. It includes the oceans, it includes lakes and rivers. It also includes groundwater and swamps and things that you don't really consider to be fresh water. So this is all of the water on the Earth. If you can see over Kentucky-ish here, there's a smaller sphere. This smaller sphere represents the amount of fresh water that's on the Earth. So this is the difference between these two is the oceans, really. So this is all the fresh water on the Earth, and it's really difficult to see because the resolution isn't really good. But there's another tiny little dot here in Georgia, and that little dot there is all of the surface fresh water on the Earth in lakes and rivers, and that's important for us as humans living on this Earth to realize, because this is the water that we drink and that we use for cooking and cleaning and everything like that. So there is a lot of water on the Earth, but the amount of water that we interact with is just this tiny little bit of water. So if we then look and say, well, great, we know that there's water on the Earth. Where else in our solar system may there be water? And there are, so here's just an image showing you some possible locations of water, and we can tell that there's water there. We can do spectroscopy and we can see the signature of water. Sometimes we don't know exactly how much water is there. That's an inference based on what we can tell about the body. But so what this graph is showing you is the relative size of the body. Like the Earth is larger than everything else here, and then the little blue dot below it gives you the equivalent volume of water on that entire body. And so you can see that the Earth does not have the largest amount of water in the solar system. That right now goes to our current understanding goes to Ganymede. It's a frozen body. The water is underneath the ice crust. Titan, we believe, has a lot of water, and Callisto, Triton, and Pluto. So the Earth, in a relative sense, doesn't have very much. And remember, as humans, we sort of interact with even a very smaller part of that. And then Dione and Enceladus satellites. And I see there's a question about the volume ratio of the water to the entire sphere of the Earth. And I'm sorry, I don't have that answer, but I can get that for you later. Okay. So where did all of this water come from? What we're seeing is that water in our solar system is maybe not that unusual, right? It exists in a lot of places. Notice that it doesn't really exist in a large sense in the local area of the Earth. So Mercury, Venus, and Mars are not on this list because they don't have a lot of water right now. Mars actually may have had a significant amount of water in the past, but because of the stripping of its atmosphere, it has lost all of that water. So,
or it's frozen internally.
Or it's frozen internally, yep. And so it's important to consider the whole system of the planet when you're thinking about what is happening with the water. So, okay, so nothing, around, not a large amount of water in our local neighborhood, but if we go to the outer solar system, then we see more water out there. Satellites of Jupiter, Saturn, we go out to Neptune and Pluto, then there's more water there. And the reason is because when the planets are forming, they form from something called this solar nebula or proto-planetary nebula. And there is a temperature gradient across this nebula. And so you can, it's kind of indicated in this image by the color. So if you're closer to the growing sun here, to the sun that's forming in the center, then it's warmer. And then as you get further out, it gets colder because you're further away from the sun. So that makes sense. And there is something called a frost line. And the frost line is, tells you at what point water can exist as a solid. And so if you're closer to the sun than this frost line, then water is a vapor and it will not condense and form a planet. And then if you're outside that, then water can be a solid and it can become part of that body when that body is forming. So it's interesting to note that for the Earth is, well, let me go out to here. So our frost line here is roughly around this asteroid belt, okay? So the Earth is inside the frost line. And so what that means is that when the Earth formed, whatever water was part of the Earth when it was forming has probably left for a variety of reasons, because it was not strongly bound by the Earth's gravity, because the sun was hotter and the solar wind was more extreme at that point. And so it really removes the primordial water from bodies in this closer in region. And so, but we know that the Earth has a lot of water, so it has been replenished after things kind of cooled down a little bit. But what has it been replenished by? And the theory right now is that it's been replenished by being hit by asteroids and comets that carry a lot of water with them and then impact the Earth, and then the water becomes part of the Earth at that point. Okay, so I'm going to switch now and talk a little bit about solar system formation and evolution. And I'm just going to say I'm a planetary scientist. This is astrophysics. It's not my forte, but I wanted to just put this into a little bit of context. So if we look at where we exist in the universe, this is not the Milky Way, because we're within the Milky Way, so we can't get a picture of it. But this is a spiral galaxy, the Andromeda galaxy, M31. It's nearby to the Milky Way, and it's a spiral galaxy like our own galaxy is. And so everything you see here is most of the bright points of light you see here are stars, but there are some satellite galaxies to M31 as well. And so what this is billions of stars circling the center of the galaxy. And our sun, is about, 2/3 of the way out in a similar galaxy. But you can see here, there's these dark areas are dust lanes. So what this is telling you is that there have been several generations of stellar birth and stellar death, because that's where these heavier elements are made, is in supernovae. And so by making these heavier elements, then you can get these dust lanes. And then the next star that comes along will gather up some of this gas and dust and will incorporate it into itself and into the planets that surround it. And so this is it's a sort of a long-term evolution. You need earlier generations of stars to have lived and died to form these heavier elements, and then you can get planetary systems after that. So I'm going to show you, this is a simulation done by Matthew Bate at the University of Leicester. And let me see if I can make it start. So it's a computer simulation. So what this is going to show you is how stars can be formed from a nebula of gas and dust. So let me see if I can start this. Okay. So the original material is not uniformly distributed, but in the model it's looked relatively uniform. But then you get little gravitational perturbations, and once you get, basically these areas are joining together from mutual gravity. And you can see the time progressing here. This is 200,000 years, which sounds like a long time, but on the scale of the universe, it's a blink of an eye. And then we're zooming in here. We're now looking at 5,000 AU, astronomical units on a side. And remember, 1 AU is the distance between the Earth and the sun. And we can see a star forming here. So all of the neighboring gas and dust is coming in and coalescing and becoming part of this star. The star, is, as you can see, is spinning rapidly, and sometimes it's throwing off pieces of, you know, some of this material that's trying to coalesce with it. And you can see these little stellar cores sort of floating away, and they'll become other stars. The other thing you can see down here, and I think we're going to recenter shortly. Yes, good. The other thing you can see down here is that this proto-sun is developing a disk of material around it. And sometimes it looks like there's maybe 2 stars or 3 stars in the system. Like right now, it looks like it's a binary star. You can see 2 stars here and a disk of material that is surrounding it. And so they zoomed out now, and so what you can see is the remnants of this large starbirth cloud, and you can see some all the way around here. You can see some stellar cores that will, you know, later on go into form into full-blown stars. And then what this will make is something that we see in the night sky called an open cluster. An open cluster is a cluster of stars that are close together physically, and also they appear to be close. And they form from the same cloud of gas and dust. If they are in, and everything that we see like this, every open cluster we see like this is in our galaxy. And so eventually they'll be sheared apart just by the differential rotation as they go around the center of our galaxy. So this is basically a stellar nursery. Everything is formed here, and then they'll eventually go their own ways and form their own families and, you know, just become middle-aged stars. So once we leave this star formation time, then we get to this next period here. And this is an image taken by ALMA, which is down in Chile. And it is of a young star called HL Tauri. This is the proto-planetary disk that surrounds this young star. And so basically what we are seeing here is a snapshot of planets forming. The star itself is in the center of this protoplanetary disk, and then each one of these dark lanes is carved out by a planet that is coalesced and is gathering material onto itself. And so as it orbits the star, it collects even more and more material, and it clears out that lane. And so you can see 1, 2, maybe 3, 4, 5, 6, 7, maybe 8 planets forming in this system. And, you know, obviously you have to wait another, 100,000 to 1 million years to see what really happens. And if any of these, you know, planets survive. But this is what our solar system would have looked like in its infancy, as it was just forming out of all of this gas and dust that was left over from previous generations of stars. And one thing that you may wonder is how common is this? And so if we look at, this is a study looking at stars of certain ages within our galaxy, and looking at how many of them have disks. And you can see that for very young stars, almost all of them have disks, planetary disks. And then as you go out, those planetary disks become less and less visible. So what has happened then is that these planetary disks the planets have formed. The rest of that protoplanetary material has been blown out by the stellar wind, and you just have the planets left over, which are harder to see when you look at them with imaging. So this is probably a very common occurrence within the universe. Stars form, they have protoplanetary disks, and they form planets. Okay, so within our solar system, what happened? We know what our solar system looks like right now, but the question is that how our solar system formed, or was there some earlier phase that then, you know, evolved into our current solar system? And there's been some work. It's called the Nice model. It looks like the Nice model, but it's the Nice model because it was done at the Observatoire de Côte d'Azur in France, and so it's Nice. And so the theory here is that the early configuration of our solar system had all of these sort of leftover little bits of planets that didn't quite, you know, coalesce into a large planet, all of these little seeds left over here. And here you can see the Sun, Jupiter, Saturn, Uranus, and Neptune. And then just because of gravitational perturbations, what happened is that Neptune's orbit kind of expanded into this ring of small bodies, scattering them into the inner solar system. And then in addition, after that, scattering them out as well. So we don't have this very thick ring of protoplanetary cores left over here. And we have something that, looks kind of like what we have right now in our solar system. So what we can think of, if we're trying to see what did our solar system form from, we can say, well, we know what our solar system looks like right now, so we can look at what they're made out of, and that will tell us. But that's not exactly true, because in the past, in the early solar system, the planets were probably more densely packed and closer to the sun, which means they were heated. And so whatever volatiles might have been there might have been lost because the planets were closer to the sun. But this whole ring here of small bodies, they never got very close to the sun. They were always quite cold. And then they were scattered even further out. So we think of this as a reservoir of bodies that have been unaltered, that really tell us what our solar system looked like in the very beginning. And so we come next to, how are we going to study these things? Because they're small and they are very far out in the solar system, and so they're faint. So let me just show you what our solar system looks like right now. So we're going to start up in this upper left, and then we're going to go around. This is kind of like a powers of 10. So we have the Sun, Mercury, Venus, Earth, and Mars, asteroid belt, and Jupiter. And then this entire square fits in this little square here. And you can see the orbit of Jupiter, Saturn, Uranus, Neptune, and Pluto with some Kuiper Belt objects. And then this entire square fits in over here. This is one Kuiper Belt object, Sedna. It has an eccentric orbit, and you can see how far out it gets. And then this whole square fits in this tiny square here. And then we see the really far outer edges of our solar system called the Oort cloud, and it's thousands of astronomical units from the sun. And it's thought that this is where the comets, long period comets, start from as little seeds within this Oort cloud that perhaps were perturbed out by, as explained in this NEOWISE model, and are just sitting out here, very faint. And every once in a while, when there's a interaction with a nearby passing star, something like that, one of them will be perturbed into the inner solar system, and we will see it as a comet. Okay, so that's what we have right now. And what we want to do then is to look at, to collect some data to try to figure out what's going on some of these bodies, what are they composed of, and that will tell us what the early solar nebula looked like. And we already know a lot, and it's because of these types of observations that lots of people have been doing for decades. And so I want to show you some of the people who are now working on it. This is my Europe group for this summer. You probably already know the Undergraduate Research Opportunities Program. That's what Europe stands for. And I have 6 Europe students, and then 2 colleagues who are working in this Europe group. Unfortunately, my 6th student had a refrigerator emergency, so he couldn't be in the image. But my Europe group is working on a variety of problems related to the things that I've just been talking about. And so I'll touch on some of those as we go. I also want to point out, I don't know if everybody has heard this, but for MIT, because of the pandemic and the fact that everybody has to be working remotely, a lot of students' internships were canceled, unfortunately. And so students at the end of the semester were looking for work that they could do so that they could learn and get experience. And so my department, EAPS, Earth Atmospheric Planetary, everybody really kind of dug deep and tried to find projects that students could work on. In a normal summer, we have between 15 and 20 Europe students, and this summer we have 93, I believe. And so there's just a lot of, we're having a lot of people working on not only problems in planetary science, but also geology and oceanography and atmospheric science. It's just a great summer. I mean, it's unfortunate what happened, but from my perspective, it looks like everybody's having a great time and learning a lot, so it's wonderful. Students at MIT also have other options to participate in research, and one of these options in planetary science is to go to the MIT Astronomy Field Camp, which is held every IAP in January, where the students would go to Lowell Observatory in Flagstaff, Arizona, which is actually where I am right now. This is a picture taken in Sedona, which is near Flagstaff. We were all going hiking on that day just to see the beautiful natural scenery. And this is just the group of students from a couple years ago, actually. This here is Taylor Seyfert. He just graduated. He was my grad student, and I'll be telling you a little bit about his work a little bit later on. So one of the ways we learn about these bodies in the outer solar system is to do photometry, which is basically just to see how bright they are and what color they are. And we can measure light curves in case they're spinning, and we can learn a lot about them by doing this. There are some large objects in the Kuiper Belt, and you can see this is an artist's conception of them. Obviously Pluto, Eris is even further out, Haumea, Makemake, and then keeps on going. One of the things that you notice from this picture, this artist concept, is that the brightness of the object is different and the color of the object is different. And if we can determine those two things, then that tells us something about what's happening on the surface. Because if you have a surface where nothing is happening and you just pop it out into the outer solar system, eventually the solar wind will interact with the ices on the surface and will make it dark and red. But there are some bodies, for instance Pluto, that has this very dark red patch here, but then it also has this very bright patch here. So what's happening, the bright areas are areas that have been recently active. So this is a recent deposition of nitrogen ice. And fresh ices are bright, and then eventually this will get darkened like this patch is here. Eris is also believed to be very bright. We obviously don't have the same kind of spacecraft images of Eris or Haumea or Makemake, but we have other ways to learn about how big they are, and then we can figure out how bright they are. And the main way we do it is something that we do in my group, is to do stellar occultations, and that gives us a direct detection of the size of the body. Besides the Kuiper Belt objects, which exist out here past Neptune and Pluto, we also have this group of objects called centaurs. Centaurs, if you think about the mythological man-horse beast, centaurs, the astronomical body, is also a kind of a combination of two types of bodies. Sometimes centaurs look like comets, and sometimes they look like asteroids. And that's why they have that name, because they have this dual nature. And centaurs, we've learned now, have actually been scattered into this region between Jupiter and Neptune from the Kuiper Belt. So gravitational interactions with Neptune scattered them into this region, and then they spend a very short amount of time here, just 1 to 10 million years, and then they're either scattered out of the solar system or they become short period comets. Now this is interesting because centaurs, if they were out here in the Kuiper Belt, they are unprocessed. They have not been heated. Nothing has happened to them over the 5 billion years of our solar system. And now they're closer to us. Because these are all really small, if they're closer to us, they're easier for us to measure. And so having this option to look at centaurs just in the Jupiter to Neptune region means that we can learn about a lot more bodies than we could when they're out here when we can't really see them. So we have a large project that is focused on looking at centaurs, seeing what colors they are and how bright they are, and if there's any rotational light curve. The other thing we can look for, though, is this other dual nature of centaurs, and we can look for a coma or some jets. This is the Centaur 29P, Schwarzmann-Wachmann 1. This is a lovely montage taken by Damien Peach over, I think it's 2 months, as this centaur moved against the background stars. And you can see over here, it doesn't have much of a coma, and then the coma is growing. So what is this telling us? This is telling us that this body has volatiles on its surface, and as it gets closer to the sun, these volatiles are sublimating and forming this coma. And so if we see activity on a body, we can figure out what distance that body is at, figure out the temperature at that distance, and then we can make a really good inference about what that volatile is. So that tells us, in a way, the composition of that body. You can do spectroscopy, but these bodies are really faint, and the volatiles may be beneath the surface, so you may not see them. But if you see this activity, then that tells you what is there. With centaurs, this was incredibly unexpected, but there's one and maybe two centaurs have actually been found to have a ring system. This is an artist's conception because we can't see it directly, but the centaur Chirico definitely has two narrow rings, which are depicted here. And the centaur Chiron may also have a ring, and this was found in some of our group's occultation data from 2013. And we can also figure out shapes of these bodies. This here on the left is the Kuiper Belt object Arrokoth, and it was visited by the New Horizons spacecraft after passing Pluto. And so what they found is that it looks kind of like two separate bodies that were stuck together. And this is probably the result of a low velocity impact, and then they did actually become stuck. These two bodies over here, however, are on the bottom. This is Churyumov-Gerasimenko, which I showed you earlier. And on the top, this is Comet Hartley 2. And you can see that each of them has this same sort of appearance where it looks like two bodies that are stuck together. My grad student, Taylor Seyfried, was working for his thesis, was working on figuring out if you rotationally disrupt a centaur, what happens to, well, this is actually work done by Sanchez and Shears, but what Sanchez and Shears found out, if you rotationally disrupt it, then it will break apart, and then these two pieces will come back together and get stuck together, and then will form another body. And so my grad student was looking at some of the things that can cause these to become disrupted. And so we think we have a pretty good theory there about why 70% of comets that we have studied close up seem to have this dual lobe nature. So where do we do all of this research? Well, one place is at the Wallace Astrophysical Observatory in Westford, Massachusetts. This is MIT's dark sky site, and I'm using air quotes because it's not very dark because it's still near Boston, but it is much darker than on campus. And so it's a lovely opportunity for students to go out here and learn how to use telescopes hands-on, and then also take data that can sometimes become part of their thesis. In addition, MIT has time on the Magellan 6.5 meter telescopes at Las Campanas observatories in Chile. And it's a very dark site, and the telescopes are very large. And so this is a great opportunity for students as well to have this, to be able to go there and use these telescopes. And then through a collaboration with astronomers at Lowell, we have also been using the 4.3 meter Lowell Discovery Telescope, which is near Flagstaff, Arizona, and you can see that here. In addition, in our group, we have been proposing to use SOFIA, which is the Stratospheric Observatory for Infrared Astronomy. It's a 2.5 meter telescope here, which is put into a 747 aircraft body. Now, the advantage, we've done several flights on this, and the advantage of this is that this airplane can fly at 45,000 feet. And you can see here, that's above the clouds. And as astronomers, clouds are our nemesis because, if you're all set to observe something, the clouds may come in and block it from sight. And so by flying on SOFIA, you're guaranteed to have a cloud-free sky. And then additionally, if you need to be in a particular place to see something like we do for stellar occultations, then SOFIA allows you to do that. So it's a really great resource that we've used several times to do some of this work. So, in this talk, just as a recap, I've talked about COMET NEOWISE, volatiles in the solar system formation, evolution, and observational studies of the solar system. And I'm happy to answer any questions now or later. I've listed my email addresses here. And so feel free to contact me, but I'm happy to take any questions right now.
Hey, Sophia, this is Juan.
Hey, Juan.
So awesome talk. So I've always been interested in how Saturn got its rings.
Yeah. So there's several theories, and one of them is that it used to be a satellite that then was pulled apart, and so it didn't survive. It maybe wandered into the Roche zone, within the Roche zone of Saturn, and so was pulled apart. or it could have been destroyed by an impact from another body. It could also be, if you remember comet Shoemaker-Levy 9, which impacted on Jupiter, comets are sort of all the time coming into the solar system and passing by these giant planets. And sometimes they hit the planet, but not always. Even if they just pass close to a planet, they can be just gravitationally pulled apart. And so if you hit a planet, if you come close to a planet at just the right angle, you can be pulled apart and then go in orbit around the planet. So those are some of the theories for the origin of Saturn's rings. And Jupiter has rings that are mostly seeded by material coming off of the satellites within Jupiter's system. Uranus has rings and Neptune has rings. All of the giant planets have rings. So probably similar formation reasons. So has anybody seen Comet NEOWISE?
No.
Okay.
Not yet.
Not yet. Well, I would say probably within the next week is probably your best shot if you want to go out and try to view it, just because it should be getting fainter. It might not, and then you might have more time, but we don't know.
Any particular location to best view it?
Yes, so you want to be, you need a really good, need a really good view of the northwestern horizon, because right now it's still pretty close to the horizon, so it needs to be clear of trees and everything. And then you want to be someplace where there's not a lot of light pollution, because the comet is faint and diffuse, and so that light pollution really affects diffuse objects. So. And I see there's a question, how is distance calibrated from space? And so Martin, maybe can you say a little bit more about that question? The distance to something, or the distance, the size of something? Okay, well, I will just answer both of those.
Probably still mute.
Yeah, I'll answer both of them.
Yeah.
We can measure the size of something on images if it's resolvable, and then so then we get an angular size of something, and then if we know the distance to it, we can just do trigonometry and figure out the physical size of something. But if we don't know the distance to something, then we need to figure out a way to know that. So if we're just talking within the solar system, then we actually use the motion of the Earth. If we're just looking at objects in the outer solar system, we use the motion of the Earth, because we know, at one time of the year the Earth is here, and then 6 months away the Earth is over here, and if we're looking at something over there, the distance to that object has changed by 2 astronomical units, and then we can see how that object is moving against the background stars, and so we can figure out where the body is within our solar system and figure out distances. If we're talking about distances outside of the solar system, then we have to use other methods. There are things called standard candles, which are variable stars, Cepheid variables, and the period of the variable is proportional to the distance that star is away from us. And so we can use those to figure out how far away things are. So I hope that answered your question, Martin.
I have a question. My question would, hello?
Yes.
My question would be, what is the current favorite theory as to the formation of the moon, our moon?
So the current theory for the formation of our moon is that it's the result of a giant impact in the early solar system, when there were some more planet cores running around in the solar system. And so one of these impacted the Earth, and then some of that material from the Earth was spun off, and the moon was formed from the remainder of this impactor and part of the Earth's crust.
Can we tell from the composition of any of the rocks that we brought back that it's similar to the Earth?
That is exactly where the theory comes from, because there is a large similarity, right? And so why would those two things be so similar? and so that's why the theory is that it has been evolved that way, because it's thinking that the Earth's crust then was, sort of, blasted off and then became part of the moon, and that's why the rocks are so similar.
Thank you.
Great,
Amanda,
that's a great question. Yeah.
Amanda, this is Paul. You gave us a pretty good presentation how the solar system was created over time. Do we know now, by studying other star and planetary system, what would be the probable evolution of that, and how it will, over time change and become something different?
Absolutely. That's a really good question, because a lot of the planetary systems that we're seeing around other stars are so compact. We see, hot Jupiters that are giant planets that are just orbiting so close to their stars, which is obviously not something that we have in our solar system. Excuse me, partly it's an observational effect, because those are the types of planetary systems that are easier for us to discover. But it's also, I know that a lot of theoretical work is going on, and I'm sorry, I'm not, on the cutting edge of that, but I know that there's a lot of work looking at, well, if planet systems form with lots of giant planets close in, can something like the Nice model happen with those as well? And then they end up being further out. And so, I think it's still early in the evolution of these theories, just because we're learning about all these types of solar systems. So I can see that there's a bunch of questions here. So let me just see if I can answer a few of them. From Tom, describe differences between the centaurs and the unheated objects much further out. Yeah, so that's a good question. I think that so the centaurs were once those unprocessed objects that are further out, and now they're in this closer in region where they can start to become, more heated, and start to lose their volatiles. And so we see that as activity, which helps us to understand what they're composed of. Eventually, when these centaurs spend enough time in this giant planet region, then they're going to lose all of their volatiles, and they'll just become a cold core, without any volatiles anymore. So it's this intermediate period. We know that they have not been processed or heated, and now as they are being heated, we're using that to tell what they're made out of. Okay, from Steve, how can you study a stellar occultation of a tiny object a billion miles away? Well, Steve, I can talk to you about that for another 15 hours, but I won't. So basically what we do is we look at the path that the object is taking throughout the solar system, and we then predict forward where is it going to be next year or 5 years from now, and what is it ever going to go in front of a bright enough star. And then if it is, then we look at we have to do very accurate astrometry to figure out where all these bodies are, so we can predict where the shadow is going to be on the Earth. Because the shadow of a small body is roughly the size of the body. So if we have like a 2,000 kilometer Kuiper Belt object, the shadow is only going to be 2,000 kilometers. So on the Earth, you have to be within that 2,000 kilometers or you see nothing. So there's a lot of prep work that goes into predicting these occultations so that we can see them. But the payback is immense, because what we get from that is we can tell with very high accuracy. We're limited actually by diffraction and not by astronomical seeing, atmospheric seeing. And so our resolution can be like 1 kilometer out at Pluto. And so what we can tell is how big the body is. We can tell if there's any surface features like mountains on the edge, if we can put a bunch of occultations together. We can tell if it has an atmosphere. We can tell what the temperature of the atmosphere is at different heights above the surface. We can tell if there's haze in the atmosphere. It's an amazing amount of things that we can learn from a stellar occultation. Selena says, what is the significance of the Oort cloud? Why is it important? Yeah, so the Oort cloud is the remnants of that solar system formation that's been sort of tossed out and exists thousands of astronomical units from the sun. It's not something that has been directly observed because it's too far away and the bodies are too small. It is inferred because we see these long period comets. Comet NEOWISE has a period of about 7,000 years, and so it is one of these long period comets, but there are ones that come with even longer periods. And so we're we are inferring from the appearance of comets that there is some reservoir out there that, that every once in a while is perturbed and comes into the inner solar system. And I know that, you know, the theory then is that other stars will have their own Oort clouds. And so I know that there's been some work, in fact, by my colleague and husband, Stephen, that sometimes these Oort clouds may mix. And so if you've got one star passing near another star, their Oort clouds may actually get to overlap. And so if we see comets coming, long period comets coming into our solar system, into our inner solar system, they may be extra, you know, they may be alien comets coming from another star system, which I think is really cool. All right, from Bob, do you ascribe to Jupiter wandering during solar system formation? I think, I'm not exactly sure what you're asking, but I think it's probably a result of the gravitational interactions with the other giant planets. Basically, once these things get close to a resonance with each other, then that sort of locks their relative positions, but until that happens, they can move around. And there have been some dynamical studies to look at what the semi-major axes of these bodies might have been before they got to their present location. And you can make a couple of things happen, and you can even make some of these initial bodies exit the solar system, depending upon the initial conditions. It's quite an interesting area of study. All right, from Tom, can we see protostars in the Milky Way that were spun off from a star formation? So we can definitely see protostars, like the Eagle Nebula is one area where the Hubble Space Telescope has taken some really spectacular images of stars forming. I think that the spinning off happens at a larger time scale, so we're not really seeing that happen. We get really just a snapshot, and you can imagine that there's some of that happening. But from that animation that I showed you, I don't know that we can definitely say that anything that we see right now is part of, you know, a spinning off like we saw in that animation. All right, from Art, are Starlink satellites interfering with your optical observations? So I have not yet, I've been lucky, I have not had a Starlink satellite photobomb any of my images, but I know of lots of people who have taken data and, you know, have lost a couple of images. These are communication satellites that have been put up in fairly low Earth orbit, and there's a large number of them. There are thousands, and there are going to be thousands more, and they're providing, you know, cell phone service and also internet service. And so, I mean, these are good services, but the satellites themselves are fairly bright. They can actually sometimes be seen with the naked eye, and they definitely can be seen by large telescopes that are looking for faint objects. And so you can be trying to take an image of, you know, this lovely galaxy or something, and all of a sudden you get all of these parallel lines going across your image from the Starlink satellites. So I know that the companies that have these satellites up there are looking at ways to make their satellites darker so they don't affect astronomical imaging as much, and I hope that they are successful. And so related is Selena's question, how large of a problem is space junk when observing stars, planets, and comets? The Earth is really surrounded by a cloud of space junk, but mostly it's very small, and it does not become visible until it enters the Earth's atmosphere and burns up. So most of it is mostly invisible to us as we're observing the universe, except for the Starlink satellites and a couple other things. Like you can see the you know, it's not space junk, but you can see the International Space Station. That's clearly not space junk, right? But the smaller things you can't see. They're still too small. And from Robert, the orbits of the planets seem to be almost circular. None are as elliptical as the comets. Does that hold up as a generalization? Is there a reason for the circularity? And yes, you're right to have noticed that, Robert. Pluto's orbit is the most elliptical of the main planets, and I still consider Pluto a planet because I worked at Lowell Observatory where it was discovered. So, but the other planets are more circular. And so I can't give you the details of this, because I'm not a dynamicist, but if you are in an elliptical orbit and there are other planets around you, then you will have different gravitational interactions with the nearby planets. And so I think it's a less stable configuration than having circular orbits. And so even though the planets may have started off with more elliptical orbits, they evolved to more circular orbits. Pluto still has its elliptical orbit because it's in a resonance with Neptune, which actually doesn't allow it to circularize. And so it's stuck there.
Thank you.
And then Stan, what is the next expected target for New Horizons? I don't know. They're looking, and I have not heard what the next target is, but I'll be interested to see, just like everybody else. Okay, and then Tom, any of the work your team does challenge the likelihood of life on objects in our or other solar systems? Yeah, that's the million-dollar question, right? And so lots of people are working on that. And lots of people are working on it in more direct ways than I am. For instance, there are some groups in the department at EAPS who are looking at signs for what do remnants of microbial life look like on Earth in the geologic, history? Like, what are signs within rock formations of microbial life millions of years ago, and can we find those when we go to Mars? And so it seemed, my initial feeling was that, well, microbial life is not going to be preserved in the fossil record, but actually in some cases you can see fossil records of things like microbial mats. And so when the various spacecrafts are wandering around Mars, those are the types of things that they're going to be looking at. And they're targeting landing these spacecrafts in areas that had been seas in the past, so they can find these geologic signs for past life on Mars. And looking for present life, that's, yes, that's the grail. And so you need to know where the water is if you're assuming that life looks like our life. Or you could, because if it's not water-based and carbon-based, then there's the whole phase space is really quite wide and more difficult for us to explore. But within our solar system, there's a lot of, it's carbon-based, and we have reservoirs of water, even liquid water, in various places. So those are the places to be looking. The moons around Saturn, the moons around Jupiter, those are targets of future missions to look for signs of life. So I'm not doing anything directly related to that, but I know lots of other people are working on that. These were all really great questions, and I thank everybody for asking them and for your attention.
Thank you.
Any other questions? Yes, so great audience, great questions. Amanda, thank you so much. We're so glad that you were able to present. I know that it was a disappointment in the last one, but we eventually got you, right? So
exactly.
And hopefully we'll be able to get you again sometime in the future. So thank you so much.
It's great to meet everybody.
Thank you, everybody. This was great.
Bye-bye.
Bye.
Bye.
Bye.